In this video, we're going to learn about the derivative property of the Fourier transform. Let's start by considering some arbitrary signal x of t. We know from our study so far that to within a hand-waving approximation, we can express x of t as a sum or an integral, depending whether or not it's periodic, but we can express it essentially as some flavor of sums of cosines. And those cosines are going to have some frequency and some amplitude and phase. And as long as we can calculate k and phi, we can effectively express our signal x as a function of cosines. Now, if that's true, what can we say is true about the derivative of x of t? Well, to work out that, we have to take the derivative of a cosine. And that's going to give us negative omega k sine omega t plus phase, which we can rewrite using the trig identity. There's a trig identity that says minus sine of theta equals cosine of theta plus 90 degrees, or pi over 2. Okay, so we can use that trig identity and rewrite this as omega k cosine omega t plus phase plus pi over 2. So if we think about this from a Fourier perspective, you can imagine that the signal that we started with x of t, suppose it had some Fourier transform a of omega. What do we have left now after the derivative? Well, after the derivative, we still basically have our a of omega, right? It still consists of the same cosines, at the same frequencies omega, with all the same basically amplitudes and phases. The only difference is that the amplitudes have been made larger by a factor of omega, and their phases have been adjusted by pi over 2 radians. So in other words, taking a derivative with respect to time has a very predictable outcome in the frequency domain. Okay, we can take our Fourier transform and just adjust it by multiplying by this omega e to the j pi over 2 term. And the last thing I'll point out before continuing is that e to the j pi over 2 is really just j. So in other words, taking the Fourier transform means taking the derivative means taking your original Fourier transform and simply multiplying it by j omega. The easiest way to see how this is actually useful is to do an example. Let's consider taking the Fourier transform of the following signal, and you can see here that we've got something that's piecewise linear, and if we were going to work this by hand, it would be fairly unpleasant. Okay, we see that over here x of t has the formula 1 plus t, and we can see that over here x of t has the formula 1 minus t. Okay, and this is x of t. So the hard way would be to say that a of omega is going to equal the integral from minus 1 to 0 of 1 plus t e to the negative j omega t dt plus the integral from 0 to 1 of 1 minus t e to the minus j omega t dt, and then we need to take the afternoon off to do some calculus. Okay, there's a lot of calculus that we have to do to resolve this down into something manageable. So my alternative approach is to say, look, working x of t is pretty difficult. What if instead we worked with the derivative of x of t? Well, what would the derivative of x of t look like? The derivative of x of t is pretty straightforward. On the range from negative infinity to 1, x of t is just a flat line, so its derivative is 0. On the range from negative 1 to 0, x of t has a constant slope of 1, so therefore it's going to have a slope of 1, like that. Then on the range from 0 to positive 1, x of t has a constant slope of negative 1, So we'll draw its slope at, its slope as, well, I accidentally deleted a lot of stuff here. Let's see what we can do about that. So this will be 1, and then this will be, here's our constant slope of -1, and then back to 0. Now, the reason why this is preferable is that I can take the Fourier transform of this by inspection, because essentially what I've got here is the sum of two different rectangles, and the rectangles, I can take their Fourier transform basically by inspection. Okay, so I can think of this as one rectangle and this is another rectangle, and we know the rectangles always have Fourier transforms that are sinc functions as long as you account for their half-width and their shift. So let's start with the green one first. So now we're, just to remind you, now we're solving for the Fourier transform of the derivative. So here we go. The green box has a half-width of a half, so it's going to be sine of omega over 2 over omega over 2. Okay, that accounts for the half-width of a half. And that box is shifted to the left by half a unit, so it's going to be e to the j omega over 2. And that box has an area of +1, so we're good to go on that. We don't need to multiply it by anything. Okay, now we'll do the second box. The second box also has a half-width of a half, so that's going to be sine of omega over 2 over omega over 2. This box is shifted to the left by half a unit, to the right by half a unit, so it's e to the minus j omega over 2 to account for the shift, and it has an area of -1, so we're going to get a minus sign there. Okay, so we're pretty close. I'm going to just try to tidy this up a little bit, and the first thing I'm going to notice is that I can factor out a sine of omega over 2 over omega over 2 out of both terms, and that leaves me with e to the j omega over 2 minus e to the minus j omega over 2, and lo and behold, this term here is really 2j sine of omega over 2. So putting it all together, it looks like what I've got is 4j sine squared of omega over 2 divided by omega. Okay, now, how is this useful? Well, look what we just decided before. Before we said, if you take the Fourier transform of the derivative of some signal, that should be equal to j omega times the Fourier transform of the original signal x of t. Well, look what I have now. I know that the Fourier transform of the derivative is 4j sine squared of omega over 2 over omega equals j omega times the thing that I'm actually looking for, a of omega, the Fourier transform of the original signal. And therefore, I can just divide through by j omega, and without hardly any trouble, I've determined that the Fourier transform of the original signal is sine of omega over 2 divided by omega over 2, and then the whole thing squared. Okay, so it's basically a sinc squared function. Alright, not an integral in sight. See how easy that was? So, that's pretty good, but I can do you one better. Let's show that we can get the exact same answer, but instead of working with the first derivative of x, what if we worked with the second derivative of x? So, the second derivative of x obviously is just the first derivative of x, and it's going to be 0 just about everywhere, x double prime of t, except at these edges we're going to get impulses. So I'm going to have an impulse here, I'm going to have an impulse here, and I'm going to have an impulse here. So let me draw those impulses for you. So we're going to have an impulse over here at t equals -1, and that impulse is going to have an area of 1, and the area of 1 is because this has a step of going up by 1. Then I'm going to have an impulse here at omega equals 0, and that's going to have an area of -2. And that impulse has an area of -2 because this step goes down by 2 units. So the down gives it negative, and the 2 units gives it 2. And then finally, over here at t equals 1, I'm going to have another positive impulse at t equals 1. Now, how is that useful? Well, don't forget that the Fourier transform of the impulse delta of t is the constant 1. Okay, the Fourier transform of an impulse is a constant. It's constant over all frequencies. So look how easy it is going to be to get the Fourier transform of this second derivative now. First, I've got an impulse. So if I do this impulse first, it's an impulse, so its Fourier transform is going to be 1. But that's an impulse that's been shifted to the left by 1 unit. So 1 times e to the j omega. Then I'm going to have this impulse. So it's going to have an area, it should be 1, but then it's, because it's an impulse, but it's scaled by -2. And then there's no time shift associated with it, so I'm going to leave it alone. And then finally we get this impulse. It has an area of 1, so its Fourier transform is 1. And then it's shifted to the right by 1 unit, so that's e to the minus j omega. And because I feel like it, I can tidy that up a little bit. The two j omega terms are going to combine together. Sorry, that's just to make it clear, that's minus j omega. That's going to give me 2 cosine of omega minus 2. And then I can use a trig identity. I think it's the half angle formula. I can rewrite this as 2 times 1 minus 2 sine squared of omega over 2. Okay, and then all of that minus 2. So that's my trig identity applied. And then that's actually going to clean it up a little bit and leave me with minus 4 sine squared of omega over 2. So that's the Fourier transform of the second derivative. So if I divide it by j omega once, I'll get the Fourier transform of the first derivative. And if I divide it by j omega twice, I'll get the Fourier transform of the second derivative. So let's try that. So a of omega is going to be calculated. I'm going to divide once by j omega to undo the first derivative, and again by j omega to undo the second derivative. And it's going to be that times minus 4 sine squared of omega over 2. So let's see, the j times the j gives me -1, which cancels out the minus 4, and that's going to leave me with sine of omega over 2 divided by omega over 2, the entire quantity squared, which is exactly the same thing that we got before. It doesn't matter how you do it, as long as you apply the derivative property correctly, you get the right answer. Now, think how much easier it is to get the Fourier transform this way than it would have been to work this calculus problem. It would have been awful. Okay, but either way you get the right answer. Doesn't matter as long as you're careful. So let's pause for a minute and try this to see if it actually works. So here's my code. Once again, as I've done in some other videos, I've defined a MySync function, which essentially just removes the pi that's built into the MATLAB's version of sync. So this ensures that MySync will just give me sine x over x. Alright, and now here's my a that we calculated. It's sine of omega over 2 squared. Sorry, sync of omega over 2 squared. And then everything else is just standard. I'm going to build this cosine. So let's give it a shot. I build it, and lo and behold, I get my triangle wave. All right. So I got the Fourier transform of this somewhat complicated signal, but I didn't have to do any integrals to do it. Okay. I let the math do the work for me. So let me give you a parting thought. When you take a derivative, it takes a of omega and converts it into j omega times a of omega. And what that means is that essentially you're emphasizing high frequencies. Okay, if your original a omega has some high frequencies in it, those high frequencies are going to get multiplied up, whereas low frequencies are going to get multiplied down. Okay, low frequencies that are close to 0, will get much smaller when you take the derivative, whereas high frequencies are going to get much bigger when you take the derivative. And that sort of makes sense, right? If you take a low frequency signal, that means it changes slowly. So when you take its derivative, you're going to get a small number. Whereas if you take a high frequency signal and take its derivative, you're going to have some very high, these things change fast, right? Those are high frequencies. So when you take the derivative, the high frequencies will be elevated. Interestingly, the opposite thing happens when you integrate. When you integrate, you're essentially dividing by j omega. And that's going to emphasize low frequencies. So, in other words, when you integrate, if your original signal had some low frequencies in it, those low frequencies are going to be even more emphasized. So, for example, if we go back to this example we're looking at over here, the low frequency signal has a lot of area under the curve, so that a lot of area is going to turn into a big number when you integrate, because integral is area under the curve. Whereas over here, each half period has much smaller area, okay, and therefore when you integrate it, it's not going to come out to be quite as much. So this is a very interesting property of derivatives and integrals that we really can only think about once we understand signals.